Right. In the previous video, I was dealing with the case of repeated real valued eigenvalues, but it had two cases, distinct eigenvalues and repeated eigenvalues. So then we had two sub cases where you have repeated eigenvalues uh, with that eigenvalue giving you distinct Km distinct eigenvectors associated with an eigenvalue of multiplicity m. And the second one, you just get one, but you need to get the other m minus one eigenvectors. And we dealt with that nice and clear. So now we then deal with the case of complex eigenvalues. And usually they come as complex conjugates. They come in pairs. Okay. So we know how to write the complex conjugates. So what we are going to argue is once you get the first eigenvalue, you only need to get the eigenvector associated with it and don't waste your time looking for eigenvector associated with the complex conjugate. It will turn out that the second one will just be the complex conjugate of the eigenvector. You don't need to compute it. So we're going to argue at some point that it's only enough to find the eigenvector associated with lambda 1, and it will then infer solutions on the other one. That is a complex conjugate. So yeah, that is what we are saying. That's what we are saying here. Now let's start with an example, and then we will develop this example into a theory that will then let you see that it's enough to just get the eigenvector associated with the first eigenvector, the lambda 1, and not its complex conjugate. All right, so here is the example, and if you solve it, you get lambda 1 is 5 plus 2i, and its complex conjugate. So let's go in there and create a system to find the eigenvector associated with 5 plus. And here is where your algebra of complex numbers is needed. So here we are. If you want, this is just the same as a 1 minus 2i minus 1, 5 minus 1 minus 2i. You are simplifying it that way. If you want, you can augment it like that, which is not necessary anyway. So all you are then doing is to then say, let me write them as a system. So you have 1 minus 2i times k1 is equals to k2. Yeah, from the first line here. It's equal to k2. And then we then now also write this second one to say 5k1 is equal to, now if you take this one to the right-hand side, it's 1 plus 2i times k2. Now we know what k2 is from the first equation. So we are substituting that k2 value the second. So we now have 5k1 is equals to 1 plus 2i into 1 minus 2i times k1. So you can bring this to the left-hand side, but you now have 5 minus 1 plus 2i, 1 minus 2i times k1 is equal to 0. Right, we need to simplify this. You can see this is 1 plus 2i multiplied by its complex conjugate. So you know when you're multiplying a complex number by its conjugate, you should be able to then now see to it that a minus bi into a plus bi should be equal to a squared plus b squared. So in this case, this is equal to, so 1 plus 2i into 1 minus 2i, this is equal to 1 squared plus 2 squared, which is equals to 5. So I can easily simplify this to 5 minus 5 times k1 is equal to 0. That's what led us to say 0 times k1 is equals to 0. So this might mean that k1 is equal to 0, or k1 is arbitrary. It's not necessarily equal to 0, but if we say k1 is equal to 0, that can send k2 to equal to 0 and it will give us a trivial solution. So we are not looking for a trivial solution. We are just looking for non-trivial solution. So k1 cannot be 0. And if we choose a k1 to be equal to 1, then we can now come here and find that k2 is equals to 1 minus 2i. Basically, we said k1 is just arbitrary. So we're going to say a k1, k2 equals to k1 is arbitrary, but here k2 is 1 minus 2i times k1. We can factor out k1 outside and say remain with 1 minus 2i inside. So we can choose now k to be equal to 1. Then this will give us now 1 minus 1 into 1 minus 2i. Now, we can separate this into a sum of vectors that have real parts and the imaginary parts. So we can separate the real parts together, and then if we want, we then say 1 minus 2 times I outside. All right. So that's your K1, but of course you can write it directly like that. For now, we want to just write it directly like that. So our solution lambda 2 x1 will then have this kind of solution. Now assume you can still do it for lambda 2 is equals to 5 minus 2i. Follow the same procedure. And K2 will then be equal to, actually, this should be 1 plus 2i, not 1 minus 2i. It should be 1 plus 2i. Please check. Please check. All right. So then when we are done like that, yes, I can see the other one is 1 plus 2i, the other one is 1 minus 2i. Yes, we then now write it like this. But you can see we have complex valued solutions. So we can make some observations here. Lambda 1 was equal to 5 plus 2i, I think, minus 2i. But lambda 2 was actually equal to lambda 1 bar, the complex conjugate of lambda 1. And the same, our k1 was this guy here. What is it? 1 minus 2i. And then you then see that the k2 is actually the complex conjugate of k1. So what it means is if you have found the k1 eigenvector, then you will know the k2, because it's just the complex conjugate of what? Of k1. So hence it will be important to then now study solutions around lambda is equals to lambda 1 and k1, and then use the fact that the other one will always give us a complex conjugate of lambda 1, a complex conjugate of the eigenvector associated with lambda 1. So instead of writing it as a x is equals to c1 k1 e to the power lambda 1 t plus c2 k2 e to the power lambda 2 t, you can write it as c1 k1 e to the power lambda 1, but plus c2 k1 bar in the power lambda 1 bar t from that observation. So basically, if A is a coefficient matrix with real entries and the homogeneous system of the homogeneous system, then if K1 is associated with an eigenvector that is complex valued, then K1 e to the power lambda 1 t and K1 bar e to the power lambda 1 bar are solutions. You don't need to go and compute the second eigenvector because we have observed that this is so in theory it's true actually what we observed from the example. So so that's what we are doing. So now we try to then extract real valued solutions from this solution here. So it lies on the expansion using the Euler formula of these two. So if we do that expansion, we find that these will be like this. The two will be like expanded like that. So all you do now is to try and extract. Remember, we said if x1 and x2 are solutions, then even the linear combinations C1 x1 plus C2 x2 is a solution also. So you can conveniently choose these C1 and C2 to give you the other solutions. So you could then say, for this one, I can call it U1, and then you get some C1 hate, C1 hate. That's another choice, C2 hate, X2, and get a U2. And you then find that some A U1 plus A2, A1 U1, A2 U2 will also be another linear combination, some X bar. And then you can also iterate on these two and get more solutions that are linear combinations that will still be solutions to the original equation. That's what it means saying the linear combination, the superposition principle. That's what it says. It says for different choices of C1 and C2, you can generate more other combinations that can give us solutions to the same problem. And that's what we want to tap on. All right, so we then now come to a point where we are now replacing this is where we are replacing, remember it's x1 is equals to k1 was 1 minus 2i e to the power what? 5 plus 5 minus 2i t. So now we have expanded this to give us C1, 1 minus 2i times e to the power 5t. Now inside is cos 2t minus I sine 2t. So now we expand this guy. This will be C1. Now we expand this guy. It will be 1 plus I 0 minus 2. And then we multiply by that bracket. And then we expand this on C1. And when we do that, we get this kind of thing here. So that's what we are doing. That's what we are doing. And we do the same for x2. And we end up with these expansions here, where we split the eigenvector into a sum of the two vectors, one a real part and the imaginary part. So let's do that and see what we do, what will happen. So then you will then find that I collect real parts together and collect imaginary parts together. So if I do that, I end up with the real parts together and the imaginary parts together. So I'll then now choose these to be constants, C1, or then call it D1, another constant. Then I'll call this one D2, in such a way that this will actually be real valid. Okay. So then if I do that, then I can now see that I can rewrite the same solution which had real value, complex valued solutions to a solution with real valued solutions. So the i's are gone. So in that case, I will then see that if I call this B1, this vector there, you can see the B1 is there as well. If I call this B2, I can see the B2 is also here. Okay, but let me identify our K1 was equal to 1 minus 2i. And we wrote it as 1 plus 0 minus 2i. Can you see that the B1 and the B2 can be identified directly from the eigenvector without going through this a this a trouble? So in other words, I could then say from the fact from the linear combinations that I would do, I can see that whatever I will get is associated with the eigenvector. So I'll then say my new real value solutions, x1 bar will be equal to b1 cos 2t plus or minus b2 sine 2t times e to the power 5t. And then you can see that the second one will then be equal to b2 cos 2t plus b1 sine 2t times e to the power 5t. And these in general now from observation would be the solutions, real value solutions associated with complex eigenvalues. So that's what we are trying to observe here. It's all about observation and getting where they are. So basically it says if we find K1, we have already gone to a point where we can identify the real value solution. So then X will then be equal to some D1, X1 bar plus D2, X2 bar. This will then be the real valued solution using the principle of superposition. All right. So that's what it is. That's what it is. So everything that we're doing here is exactly what I was summarizing there. And this becomes our new solution. So in general, we can summarize now that if we have a complex eigenvalue, lambda is equals to alpha plus beta I, where beta is greater than 0, then the first solution x1 will be equal to k1 in the power lambda I is just given by this guy here. And then when you then define b1 to be half of k1 plus k1 bar. In fact, if you do this, you get the real part of k1. And then b2, if it's defined by this, by the way, even if it is I here, it is real valued. It will give you the imaginary part of k1. And once you do that, then the solution, the real valued solutions can be found. And they are linearly independent, actually, and their solution to this. Remember, this is not a prime, it's just x, the homogeneous solution. So That's how you get real value solutions from complex valued eigenvalues and complex valued eigenvectors. So there we are. We have it. So we can solve this problem here. It definitely gives us complex eigenvalues, but we've added the aspect of finding the constants of integration. So now this one will give us lambda equals plus is 2i. And of course, this will be minus 2i if you take the complex conjugate. Now we're just going to focus now. Instead of finding the eigenvector associated with 2i and the other one associated with minus 2i, we just do it for 2i. Because we have made observations here that it shows that it's not necessary to get the second one because it's always the complex conjugate of the one that we have computed already. Okay, so let's do this. Divide by 2, so row 1 goes to 1 over 2, row 1, and then whatever you want to do here. But all you will do is to then say use the last row. Your k1 is equals to 2 plus 2i. It's minus 2 plus 2i k2. Okay, so if you choose k2 is equals to minus 1, then you have your k1 there. Right. Check that it satisfies also the first equation. So you are solving systems of complex numbers. But this one will then reduce to that part. When you just use k is equals minus 1, it's just a way of avoiding the negative values. You can choose k is equals to 1 also, but I'm just trying to deal with that negative value. So I, but by avoiding it here, I'll still introduce it there, no problem. So this is our eigenvector, and we can write it in terms of the the real part and the imaginary part. And imagine immediately I now see where what my B1 and my B2 are. I've identified them, and I can see here that lambda is equals to 2i means 0 plus 2i. Remember, this is alpha, this is beta. I can see what my beta is, what alpha is. So we won't have e to the power 0t, alpha t. It's just 1, isn't it? So I'll then go and say, from the formula of observations, we then see that x1 is equals to b1 cos 2t minus b2 sine 2t. And then the sum b2 starts here with cos 2t, and then but it's now added to b1 sine 2t to get x2. And as a result, my solution now becomes C1 times X1 plus C2 times X2. And if you want to expand, you get this just being fenced, but you could leave it there. Now you want to apply the initial conditions. So you are saying X of 0 is equals to 2 minus 1, then it is equal to, so you then now put T is equal to 0 here. T is equal to 0 there. T is equal to 0 there. And you will then find that it's C times that guy and that guy. So you can now form an augmented system for C1 and C2. If you want, you can easily see that this system is just 2 minus 1, 0, and 2 minus 1. I can easily solve it nicely. A minus k1 minus c1, sorry, is equals to minus c2. Is that so? Yeah, is equals to minus 1, sorry, which implies that c1 is equals to 1, just from this row here. Then I can now have 2c1 plus 2c2 is equals to 2. And then it says here 2C2 is equals to 1 after substituting and putting it on the right hand side. It's equals to 0, I think. Yes, because this is 2 minus 2C2 is equal to 0 and C2 is equal to 0. So you might not even need to do the row operation if it's straightforward like that. And let's see, that's exactly what we are getting here, even if we do row operations. And at the end, the final solution is determined by the x1 terms because C2 is now 0. All right, so that's how we deal with this case of complex valued solutions. And then you'll find that there's tutorial questions that you need to solve. And these tutorial questions will actually give you complex valued solutions, and you need to deal with them and they also deal with the initial value problems. Okay, so that's and then you have more problems here to work with. Probably this will cover all the three cases of real valued solutions, distinct, repeated, and then complex valued. So make sure that you solve every problem that is given on this because it helps you to process through the notes that we've been going through. All right, thank you. I'll stop here.